Okay, so if you had to explain what a transducer was, Emily, to your child, how would you explain it to her?
I would tell her that it is a device that will like a sonographer transducer. Well, duh, right? I tell her that when you put it on your skin with a coupling with the gel, you would be able to see her insides.
Okay. What about you, Gold? And we're talking about your younger one.
Oh, my younger one?
Yeah,
Oh
so
my
the
gosh.
cute one.
Oh.
Your older one's cute, but she's adorable.
I would say, like this transducer is like a camera, but it doesn't have a camera. It's like the sounds, like make the picture. I don't know how to explain it to her. She's,
Okay,
it's
so
hard.
What if you were explaining to your dogs?
No.
Roof, roof, roof.
I guess you have a device that.
I'll try.
Oh,
Alright, so I'll say like, okay, so Mija, like this is a device
Me.
that that has crystals inside of it. So when you plug it into the wall or the outlet, it vibrates, and those vibrations let us see inside of the person's body, and those vibrations bounce back off of your body and go back into the device, and it shows us image on the screen.
And your kid will be like,
and then why?
what's vibration?
And then be wise, so be
Yes, because every time you explain something to your kid,
Why? What? What's
so we
that?
can see if you're normal, if your insides are normal.
Why?
Yeah.
Okay, so yeah, so, see how we were all describing our points of view of what a transducer was? This is what a discussion question should look like. Okay, because I know what a transducer is. I know what the piezoelectric phenomenon is. I know what the Curie point is. I know what a CMOS transducer is. I don't need to see what ChatGPT's definition is. Okay, I want to see what you guys have to think about it and how you would use this to your benefit. Okay, this is what I was looking for. Okay, the piezoelectric effect. Okay, so this is what the ultrasound transducers are based upon. Okay, so what did we learn about the piezoelectric effects of these?
Crystals.
Whenever there's like energy to the crystals vibrates.
Okay, why is there vibration?
Why is it vibrating?
Yeah.
Because of the mechanical energy going into electrical energy.
Okay, so that mechanical energy is what causes, or is a vibration, and the electrical energy causes that mechanical energy. But how is that doing that? How does it vibrate? What's causing it to vibrate?
Pressure?
There's a pressure difference for sure, but what's happening within the crystal that's causing it to vibrate?
It's expanding.
But why is it expanding?
It's being reshaped or distorted.
Why?
Is it the poles?
The poles, what's happening with the poles?
The electrical pulses.
They're moving around, right? They're moving around. These poles, okay, every molecule has its natural state, right? So, let's imagine a bag of steel marbles, right? Okay, so if we put the marbles on the table, that bag would shape the way that the marbles fall, right? Okay, so let's say that the bag of marbles falls on the table, the bag is now flat, right? Okay, now if I pick up the bag of marbles, what would the shape be of the bag?
Like a teardrop?
it'd be like a teardrop, right?
Mhm.
Because of the mass that's on the bottom.
Mhm.
Okay, now, what if I took a strong magnet and I put it over my hand? What would the shape of the bag be now?
An upside down teardrop.
An upside down teardrop, because all the balls would go to the top and nothing would be at the bottom, right? Okay, so what happened to our bag in that movement?
Got distorted.
It was distorted, okay? That's why, okay? Those molecules were in their natural position, but when there's a charge or there's a voltage applied to it, it causes those poles to move around with the
But-
crystal.
The crystals are already polarized, right?
In a transducer and a PZT, or, okay, like the PZTs and quartz. Okay, let's say that we made a PZT crystal here, we would have to polarize it.
But the ones in the
Yeah,
lab, they're
degrees.
Oh, yes, yes, all of the ones that are functioning as an ultrasound transducer have been polarized.
So, well, cause the Curie point, it polarizes it and then it cools down and they get set in that shape, right?
Okay, almost. So the Curie point itself doesn't polarize the elements or the crystals, okay? What the Curie point does is it causes that crystal to expand, and then there's a charge put to it, either negative or positive, that causes the poles to swing around towards that magnet, and then it's cool, and then they're trapped in that
So
position.
that's how they're trapped in that position in the transducers, and the electrical charge just kinda like makes them move.
Yes, it just makes them vibrate. Okay, so, you know, like the cartoons, you know, when like the cartoon gets shocked, what happens to that cartoon? It gets electrocuted and they shake, right, Riley? It's the same thing that's happening to the crystal, okay, it's being electrocuted. Okay, so, explain it to me again.
What piezoelectric?
Huh?
So they're crystals that vibrate,
And why do they vibrate?
they're distorted.
Okay, so the crystals get distorted, yes, but why? Because the molecules within the crystals are vibrating, they're moving within the crystal itself, so that causes the crystal to vibrate. Okay, so the molecules that are within the crystal are being interrupted, okay? They're being shocked and they're violently vibrating back and forth, which causes the entire crystal itself to be distorted and causes a vibration. Okay, so what happens with that vibration? Why is it important that we have a vibration of the crystals?
So it can send out the sound waves?
Okay, so that vibration is a what? What type of energy? Mechanical energy, right? And what does mechanical energy do?
Sensitive energy.
Propagates.
So that vibrates.
It propagates, right? Energy propagates, okay? So if they apply an energy in a forward motion, that energy is gonna continue to go forward, right? Okay, now it bounces off our liver, then what happens? It makes the crystals vibrate again at that frequency that it sends out, and then what happens? And then it turns to electrical energy, and then what?
Displayed on the screen.
And then it gets interpreted by the machine, okay? And then it gets displayed on the screen. Okay, don't forget that essential part, because it has to be interpreted,
Yeah.
okay? Because if we didn't have an interpreter, then it would just come out like a beep. Okay? Okay, so we went over the mechanism. Okay, piezoelectric mechanism, exactly what happens. So we can see here that the molecules within the crystal itself are expanding and contracting, which make the entire crystal expand and contract. Okay, does anybody have a diamond? A real diamond? No?
Oh,
Gold?
like the ring?
Like a ring?
Let's
I
test
think
it.
you had some diamond.
I have a diamond tester. Let's test it.
I didn't wear it today. It's very small.
Why you take it off, bro?
That's beautiful. Okay, you see this diamond?
No.
Okay, do you guys know what the diamonds are made out of?
Oh, carbon.
Carbon, right? Okay, densely spaced carbon, right? It's been compressed so much that it crystallizes. Okay, so if I were to throw this on the floor, which I'm not gonna do. Nothing will happen to the crystal, right? But the ring itself would bend.
Yeah.
Okay, so do you think it's easy to manipulate a crystal?
No.
No. So that's why the machines function with megahertz. Okay, what does mega mean? Millions. Okay, millions of voltage of electrical energy applied to a crystal that causes that crystal to vibrate. Okay, can someone look up how much electricity it would take to kill someone?
The trans.
I forget.
If someone looks up my history after we put amputate,
That would be very unfortunate. Like, God forbid that someone that you know gets struck by lightning. And
With
that's
the
not their
taser?
history.
it says 50 to 150 milliamps.
Milliamps,
Milliamps.
you can convert that into hertz. Well, yeah.
Convert to hertz.
Yes. Okay, polling. What is polling? Victor?
It's like the natural, what do you call it, like positive and negative dipoles that
Yeah.
elements have.
Yeah, so poles are positive, negative, right? Okay, so they're the types of energy that are attracted or emitted, right? So a magnet has two sides. It has a positive pole and it has a negative pole. Okay, the Earth has two poles, North Pole, South Pole. Okay, America has two poles, Republican, Democrat. Right? Ultrasound, passing, failing. Okay, those are all poles. Okay, so do we want our crystal randomly set or do we want it poled? Poled. Okay, so does that mean that we can't get the piezoelectric effect when they're like this?
No, you still can.
You still can. Yes. So we can still get a charge and we can still get vibration if the poles are randomly placed. Okay? The only thing that polling does is it makes it more efficient. Okay? It's easier for the machine to get that vibration, and on top of that, it's a calculated and predictable vibration. Okay? Which means that we can apply a certain hertz to a setting. Okay? And how do we achieve this?
By heat.
It's a Korea.
Okay, Curry effect. What does the Curry effect do?
It heats it up,
Expands
expands
them
it,
and
and
aligns
it will
them.
split
Okay, so what is it expanding?
the crystal. The atoms.
Okay, no, the crystal itself. Okay, so the crystal itself expands, and then what happens?
The atoms
An
go.
electrical charge.
And the electrical charge, and then what does that do?
Pulls the.
Just get it over with, Andrea.
Pulls the crystal.
Thank you. Okay, so what does that charge do?
It polarizes the crystal.
It's polarizing, right? So if we have a positive charge on the crystal, what pole will be towards the positive?
Negative.
Negative. Why is that?
Because
Opposites attract.
Because the opposites attract. Okay? Did you find out?
It's not, it doesn't say.
No.
It says there isn't much information about converting 150 milliamps to hertz.
Okay, yeah, they're just different forms of.
It just says frequency difference.
Okay. Okay, so polling, good or bad?
Good.
Good, okay. Without polling, will we have an ultrasound transducer?
Yes.
Mm.
Yes.
Well, now
You
It's not as
can.
energy efficient.
So you can, but what would happen if we heated our crystals past the Curry point on the transducers?
The polarize.
And they wouldn't work anymore.
They would depolarize and then they wouldn't work anymore because they have a specific amount of electrical energy that's applied to it. Okay? Is there any questions over the first PowerPoint?
No.
Okay, again, Vanessa, what's a transducer?
A transducer is a device that turns one form of energy into another.
Beautiful, okay? So, on our ultrasound transducers, how do you do it?
It turns electric potential energy into mechanical and then back.
Okay, very good. Okay, so there are so these are the basics, okay? These are the fundamentals of an ultrasound transducer, okay, of a PZT transducer, okay? And what is PZT?
Physiology.
No.
Lead zirconate titanate.
Yeah, somewhere, yeah.
They're human-made, crystals,
Do
okay?
you
They're,
know what it's made out of, just memory?
I mean, yes, it's man-made, okay, this does not occur in nature naturally, okay? They're fabricated, okay? Because they're easier to reproduce, they're easier to make one dimension, or make it bigger, make it smaller, propagation speed is set. If we got crystals from nature, we would have to be very specific on the crystals that we would get. It would be really ineffective. Okay, so these are the basics. We got the case, what does the case do?
Protects the inside.
Protects the inside, and holds everything together, right? Okay, we have the electrical shield. What does that do?
Keep electrical noise out.
It keeps electrical noise out and the stuff that we want in the probe, right? Okay, the acoustic insulator.
Keeps the sound, like.
Vibrations out.
It keeps the sound energy out
And
and it keeps the vibrations that we want in the transducer. Okay, and we have the PZT or active element. What is that?
The crystal.
It's a crystal, and what does the crystal do?
Vibrate.
Vibrates, making mechanical energy that is propagated through the body, received, and then transferred into an electronics signal, right? Okay, we have the wire. What is a wire?
Provides the electricity.
Provides the electricity to the transducer. Is it just one wire, or does each crystal have its own wire? Each crystal has its own wire. Okay, so if we have 250 crystals, how many wires do we have?
So we need to
Right. They're proportional, right? Okay, the matching layer. What is the matching layer also called?
Footprint.
Footprint. Okay, why is it called the footprint?
It's the outer layer.
Because the material used is like the same as the skin. Mm.
So if I'm walking in mud and I'm stepping, what am I leaving behind? Footprint. Okay, so how can I tell what size of shoe I was wearing?
Oh, is that what makes the shape of the screen? Or no?
No.
No.
It's the size, okay? It's the size, it's a beam width, okay? The footprint or the matching layer is the diameter of the sound beam. Okay, it's a footprint, okay? When you go to a store, how do you know what shoes to buy?
No, my
Measure your
size.
foot.
Because it has your size and you measure your foot, right? Okay, so that's how we know what size of transducers we have. Because it's the footprint, okay? What is it made of? Do you know?
Silicone. You said
Plastic
plastic
silicone?
material.
Plastic
Skin.
material?
Deer skin. Deer skin.
No, okay, but you're really close to hitting the mark that I want you guys to hit.
Skin.
Okay, so so it's made out of a material that has a similar impedance to skin, right?
Yes.
Okay, and why do we need that?
So there's no,
Reflection.
from the air.
When there's no reflection, okay? Or not so we can say reflection, but what really happens with air molecules?
The scatters.
Scatters, it scatters, okay? I know why the book says reflection, okay? It's really scattering, okay? And why is there scattering?
Is less.
Because the wavelength of sound is bigger than the molecule of air, which causes it to go in unpredictable directions, right? Okay, so what does the matching layer do then?
It facilitates the transmission of sound.
It facilitates the transmission of sound into the patient's body. You can answer anymore. Okay, so what do we use in between the matching layer and the skin?
Gel.
Gel. Why?
Because it helps transmission of sound into the skin.
Exactly.
And
Like
Like,
the matching layer.
And overheating.
Okay, so and it helps the propagation of sound into the patient's body. And why do we need propagation of sound into the patient's body?
to be able to see
So you wanna see, are we actually looking inside the patient's body?
or listen.
Okay, so we need propagation of mechanical energy or sound into the patient's body to receive echoes. Those echoes are then received by the transducer, they're interpreted and displayed as an image on the screen. Okay, so the matching layer and gel increase the efficiency of the sound transfer between the transducer's PZT and the skin. Okay, so with this statement here, what can we say about the attenuation between the PZT and the skin? Or the impedance?
Well, without the gel, it's a big difference.
Difference, that's the word right there. Okay, so we can say that the impedance between the PZT and the skin, that there's a big difference, right? Or we can say that the attenuation between the crystal and the skin, that there is a big difference, okay? Okay, so the thickness of the matching layer is 1/4 the wavelength of sound in the matching layer. Okay. Does that make sense to everybody?
No, not really.
Okay, so if we know that the matching layer is 0.2 millimeters, what's the wavelength?
Okay, say it again.
0.8.
Okay, so if our matching layer is 0.2 millimeters, what's our wavelength?
0.5.
How'd you get 0.5?
That's
0.05?
1/4.
You multiply it, right?
You multiply it.
Yeah, you multiply 1/4 times 0.25, cause it's 1/4. Right? I got
You
0.
lost All right.
Cause
so
1/4 equals
it's-
0.25.
No, so it's 0.2, right?
Yeah, 0.2
It's 0.2,
times
No, 0.05, yeah, that's right.
0.05. Cause 1/4 is equal to.
No, well, yeah, no, but you're multiplying it by itself, the 1/4, cause it's 1/4. So how many fourths are there in 1/4? 4. 0.2 times 4 is
8.
0.8,
Oh, so good.
yeah, 0.8. Okay, do you understand that?
No,
Yes.
this,
Yeah, okay,
Oh, I get you.
so you have the right process, you just have the wrong number.
okay.
Okay, so, from here. That's 1/4, right? Okay, so we know that the matching layer thickness is 1/4 of the wavelength, okay? So this is our wavelength. And I said that our matching layer thickness is 0.2, right?
Mhm.
Yes.
So 0.2 plus 0.2 plus 0.2 plus 0.2 equals 8, or 0.2 times 4 is 0.8.
Oh.
Okay, so our wavelength is equal to 0.8 millimeters.
Yeah, that makes more sense.
Yep.
Mm-hmm.
Okay, now, the thickness of the active element is 1/2 of the wavelength of sound in the element. Okay, so if our thickness of the active element is 0.2, what's the wavelength of sound in the element?
0.4.
It's a half of 0.2.
No,
Oh.
it's the same thing as that one.
It's the same big thing?
0.2 times 2 is
0.4.
0.4, yes.
Oh.
It's half, okay? How many halves are there in one? There's 2. 0.2 plus 0.2 is 0.4. I think you guys are making it up.
So I think-
I just think that should be.
Like if we did the same example that you showed us earlier with like just the two waves in 1.2, 1.2. It's just, that's what
Yeah.
makes it easier for me.
Yeah, that's all it is. Okay, so you want me to do that one? Is that what you're saying?
I can do it.
No, like, did you want me to make an example of?
Oh, yeah.
Yeah,
Well, cause on the notes from last time, I did put 0.25 for the matching layer.
yeah,
And then-
but that's on the other slide, right?
No, it was for the matching layer.
Yeah, I know.
So
Oh,
what
he
was it?
fixed, did you change the content?
Well, good turn. Hang tight. I'm confused. Okay, backing material. What does the backing material do?
It absorbs.
No, it stops the vibration of the.
It stops the ringing.
It stops the ringing of the crystal, right? Why do we need the ringing to stop?
Shorter
Shorter pulses,
pulses.
okay? And what does shorter pulses do for us?
Improve
Improves
the
axial
axial
resolution,
resolution.
right? Which makes what? Our picture look better,
Mhm.
okay? So, but what's the downside to using the backing material?
Oh, those are the 3 in the bottom.
Okay, so let's start with decreased sensitivity. Okay, so before we move on, everybody knows what backing material does, right?
Yes.
Yes.
It stops the vibration. Yes?
Yes.
Okay. It has 3 main consequences. Those are decreased sensitivity, wide bandwidth, and low quality factor, or low Q factor. Okay? We're good with this?
Yes.
Okay, so decreased sensitivity. Why is decreased sensitivity bad, Victor?
Because you want to be able to distinguish like the lower whispers or echoes.
Yeah, lower echoes, and whisper is a good way to put it. Okay, so the machine talks, bounces off, and it listens, right? Okay, but it's listening to my voice at a normal frequency, okay? But sometimes there's whispers, okay? There's low intensity echoes that help us identify pathology, okay? Like the example that I gave you guys, if we have an abscess and the sensitivity is set too low, then we are not gonna be able to see those low level echoes of the pus within the abscess, and it's gonna look like a simple cyst. And is a simple cyst okay?
No.
Yes. Simple cysts are fine, okay? It has to be a simple cyst, so it has to be round without any internal echoes.
The star.
Huh?
No.
Yes, yeah. Okay, now, an abscess, is that okay?
No.
No.
No, what does that indicate? Infection, and infections are bad, right? And they can get worse if not taken care of. Okay, so if our settings are off, we can misidentify an abscess for a cyst. Okay, so that's one of the downsides of what?
Oh.
Of having the backing material, okay? That's the main one with decreased sensitivity. It also has to do with Doppler, okay? Remember that example that I gave you guys of a person that had really poor blood flow in the lower extremity? But there was still flow, okay? But because our settings were off, we misidentified that patient having no flow, and then now they chop that patient's leg off. Okay? So, I know that it seems exaggerated and drastic, but it does happen, okay? Okay, why bandwidth? What's a bandwidth, Andrea?
That I was having a hard time understanding yesterday. I just know that if it's one frequency, then it's a narrow bandwidth, and if there's a difference in frequency, then it's a wide bandwidth. So,
Yeah, that's exactly it.
It's kind of like the amount of information in a given time.
It's the amount
The frequency.
of frequency that's given by the crystal at that point where it's dampened.
So it's not the amount of frequency pulses getting out? Or
Well, yes, but what's causing that change in frequencies?
Backing.
the backing?
The backing material, okay? I forgot to bring my ukulele in.
I have my tourniquet.
What's that?
The tourniquet?
Oh, there you go, turn it. I heard turkey leak. I'm just really hungry. hold it like that, okay? Sounds like club music. Okay, it has the same note, right? Okay, and you see, alright, it's not gonna work. Okay, so it has the same note, okay, consistently, right? Like continually. I'm consistently hitting this one, it's making the same note. Okay, but if it did this and I stopped it, it's going to pick up all of the vibrations from up here to down here. Okay, that's a bandwidth. It's gonna pick up all of these frequencies. Instead of just this constant one, if I put my hand down here, it's going to stop, but it's gonna vibrate, right? And then it's gonna stop. Okay, so all those little vibrations are being picked up by the machine. Okay, so that's a bandwidth. Okay, so the bandwidth consists of all of the frequencies that are being emitted by the crystals. Okay, so if I told you guys that the highest frequency that was emitted was 10 megahertz and the lowest frequency was 8 megahertz, 2 megahertz, man, I gave you 10. What's the bandwidth? Okay, 8, okay. Now, if there was 5 and the lowest was 5, what's our bandwidth? 0, okay. So what type of probe is a 0? Continuous wave, right? Because it's just 5. And what type of probe was an 8 megahertz bandwidth?
Pulse wave.
Pulse wave, okay? So which one has a, okay, so you guys understand it. Higher bandwidth is pulse wave, lower bandwidth, continuous wave. Okay, so having a wide bandwidth can reduce axial resolution, okay, which can make our image look blurry, okay? It also affects the penetration as well. It has compromised contrast resolution, okay? And what did we say the contrast resolution was? Compare what? Can you pass this to
Different structures or tissues?
What's that?
Comparing different tissues or different structures?
Yeah, different tissues. Okay, so what do different tissues look like?
Fat.
Come on, you guys are sonographers.
Gray?
Oh, like on the
Yeah,
screen?
on the screen.
Oh, like hyper.
Okay, so let's say that the liver, right? So what difference does the echogenicity of the liver have with the diaphragm? It's hypocoic to the diaphragm, right? Okay, now if we have poor contrast resolution, we can't tell the difference between those two types of tissues. Okay, it would just look like one tissue.
Okay.
Okay, if we have improved contrast resolution, that means that we can tell the difference between the liver and the pancreas. Because they're pretty ISO, right? Well, I think yours is pretty hypercoic, even though you say that you don't drink water.
You drink a long time. I just saw you one.
Okay. So low Q factor. Continuous wave transducers and therapeutic transducers have a narrow bandwidth and have a higher quality factor. Okay, so we can say that pulse wave transducers have a wide bandwidth and a lower quality factor. Okay, and how do we find the Q factor?
Mean frequency divided by bandwidth.
Okay, so let's try the continuous wave example. Okay, so we have 5 megahertz is the highest and 4 megahertz is the lowest. What's our bandwidth?
1
One what?
megahertz.
1 megahertz, okay? And what's our main frequency?
5.
5, okay? So it's 1/5 or
0.2.
2.2. Okay, now let's try the pulse width. Okay, so let's say that the highest frequency or the fundamental frequency is 5 megahertz, but our lowest is 1 megahertz. So what's our bandwidth? 4. Okay,
Oh, yeah. Okay.
so the 5/4 is what?
1.25.
Is there like a quality factor
What's that?
or is there a quality, I mean, a unit?
There's not a unit. No, quality factor is a unit that's number.
Well, right now you said pulse wave is equal to, what was it,
Wide bandwidth and low quality? You said 5 over 4 was the answer?
Yes, yeah, because it's a main frequency, which was 5, and the bandwidth was 4.
And then there's no, unit for that?
No unit.
Bandwidth?
It's just Q factor is equal to whatever the number is.
Bandwidth
So
units
megahertz,
in
right?
millimeters?
No,
Or no?
megahertz.
Megahertz.
It's megahertz. Well, it's hertz or megahertz, whatever the unit is of the sound, of the frequency. Okay, so we have transducer frequencies. And okay, so in continuous wave transducers, what determines the frequency?
Electrical frequency.
The electrical frequency. Okay, in continuous wave, electrical frequency is equal to acoustic frequency. Does everybody understand that? Okay, so if we have a 5 megahertz ultrasound system, the acoustic frequency on the probe will be 5 megahertz. Okay, they're equal. Okay, now in pulse wave imaging, there's 2 factors that tie into frequency, or that determine frequency. The speed of sound in the PZT and the thickness of the PZT. What's the PZT? Crystal. Okay, so if we have a high speed of sound in ultrasound, or sorry, if we have a high speed of sound in the crystal, what's our frequency gonna be? No, high.
They're directly,
They're directly related.
speed of sound is directly related.
Speed of sound and frequency are directly related. Okay, so if we have a low propagation speed in the crystal, what frequency do we have?
Low frequency.
Low frequency, okay? Speed of sound and frequency are directly related. Okay, so the speed of sound in most PZTs is 4 to 6 millimeters per microsecond. Okay, now we have the thickness. Okay, so thickness and frequency have what type of relationship?
Inversely.
They're inversely related. So the thicker the thickness of the element, the lower the frequency. The thinner the thickness of the element, the higher the frequency. Okay, so taking that information, what type of crystal do you think curvilinear probes have? Thick?
Thick.
And what else?
Oh, no.
Low frequency.
With a low speed of sound, right? Which creates a lower frequency, which allows for more penetration, right? Okay, inversely, what type of crystal do you guys think a linear probe has?
Thin.
Thin crystals
Higher PCT speed.
and a higher PZT speed. Okay, so the equation for frequency is frequency megahertz is equal to the PZT sound speed divided by 2 times the thickness in millimeters. Okay, you will have to calculate this equation, okay?
And you do the multiplying first, right?
You do the multiplying first. So the thickness of a pulse wave transducer is equal to half the wavelength of sound in the PZT. So yesterday, I did the wavelength is equal to the thickness, not the thickness is equal to the wavelength. They're different. So that's why it was division yesterday instead of multiplication. It could be either or. If you have information for one, then you can get the information for the other. So if I told you that the wavelength is 0.2, then the thickness of the transducer would be 0.4. Okay? And if the thickness of the PZT was 0.4 millimeters, then the wavelength would be 0.2. Yep.
When we divide this, when we're looking for the PZT,
The wavelength.
the wavelength.
Okay, so the test tomorrow will be the same format as the previous tests, okay? It'll be true or false, multiple choice. I don't know if there's gonna be matching yet. And, multiple choice and, short answers.